It's my pleasure to introduce Professor Alvaro Lozano-Robledo for our series in the public talk and number theory at the number theory unit at the Center for Advanced Mathematical Science at EUB. I just want to give a little introduction about Professor Robledo. He's a professor of mathematics at the University of Connecticut, as is currently a visiting scholar at Harvard University. He received his PhD from Boston University in 2004. After temporary positions at Colby College and Cornell University, Professor Robledo has worked at the University of Connecticut since 2008. His research is in the area of arithmetic geometry. He has published 2 books, Elliptic Curves, Modular Forms, and their L functions, and a book on number theory and geometry. Professor Robledo's blog, A Field Guide to Mathematics, contains other short stories and also other pieces of interest to mathematicians. Welcome, Professor Robledo, and the floor is yours.
Thank you very much. Thank you very much for the introduction, and thank you for the invitation to speak here. It's really an honor. So today what I would like to do is some sort of introduction to elliptic curves with some history, but especially just explain the central role of mathematics that elliptic curves play. So I'd like to start with a quote by Serge Lang, who was, by the way, my academic grandfather. So my advisor's advisor. He wrote in a book that it is possible to write endlessly on elliptic curves. This is not a threat. And I'll start with the same non-threat, that there is so much one can say about elliptic curves. So this is just really the tip of the iceberg of elliptic curves in mathematics. But what I really wanted to talk about is we'll get in a minute to what are elliptic curves and what they aren't. But we want to talk about, are they really everywhere? And I'll explain that they're really, really everywhere in very surprising instances. For example, I don't know if you are a gamer or if you have kids that are gamers. In 2010, for example, the PlayStation 3 was hacked, and bootleg video games were able to play it on the PlayStation 3. And elliptic curves were to blame, or people who didn't know enough about elliptic curves. So this is a good reason to learn about elliptic curves. Similarly, in 2013, there was one of the first Bitcoin heists. And the reason for this, again, was not a deep knowledge of elliptic curves, in this case, elliptic curve cryptography, which I hope I have a chance to get to today. So, but elliptic curves, they also appear in more mathematical senses in very surprising ways. For example, this number is, well, it's a very large number, it's a real number, and by no stretch of the imagination, it should be this close to an integer. This number is a transcendental number that follows by a theorem of Gelfand and Schreider. So a real number that big, that is so close to an integer, why would that be? And it turns out that elliptic curves are to blame. There is an elliptic curve that I'll talk about later that explains why this number has to be so close to one integer. And in fact, it explains why it has to be this close to an integer. But in other circumstances, just more very, very usual things in number theory. For example, this polynomial is well known in number theory because it takes prime values. For the first 40 values, for starting from 0 up to 39, you get prime numbers. That doesn't work for 40 or 41, but actually the factorizations of those numbers are also interesting. But the fact that these are all prime numbers, it is also related to elliptic curves, to a certain elliptic curve. And it turns out it's the same elliptic curve to blame from the previous slide. So, but not just that, the elliptic curve, they really appear, of course, in number theory, but they play a central role in algebraic geometry and complex analysis. They show up in topology. They play a surprisingly central role in some of the applications of logic in the 20th century and nowadays. They show up in group theory, but also outside of mathematics. They show constantly in physics and computer science, in art. So why is that so? So what I want to argue today is that elliptic curves show up in so many places because they are in the sweet spot of some of the very central topics that we study in mathematics, for example, in arithmetic, in geometry, in complex analysis, in complexity theory, and in some way, and there's the sweet spot of our cognitive ability to deal with mathematical problems. So I'll talk about that too, and what I mean by that. So for example, so why are they in the arithmetic sweet spot? So in particular, what is an elliptic curve? To answer that question, it's actually better to start with the question of what is a Diophantine equation, so we can place elliptic curves in their context in terms of number theory. So Diophantine equations are actually some of the simplest equations. They're polynomial equations with integer coefficients. And our interest in these comes from, well, number theory problems or number theoretic problems, where we're trying to find solutions to these types of equations with the values of x and y, for example, here, integer coefficients or rational numbers as solutions. This is Diophantus's, the cover of Diophantus's the Arithmetica of Diophantus, which has a lot to do with this topic, because so more generally a Diophantine equation is a polynomial, some polynomial in several variables with integer coefficients, and that was the topic of Diophantus's book. So Diophantus of Alexandria, who was born around the year 200 of our era, is known sometimes as the father of algebra, and he's known for that series of books I'm talking about, Arithmetica. He wrote other books. We know that there are other books he wrote, but they have not survived, or we haven't found copies of. And Arithmetica it was great because it was the first systematic study of Diophantine equations, and it was used as a textbook of arithmetic for quite a long time. And that's, for example, why Fermat was studying Diophantus's book even much later in the 1600s. And well, if you get bored, you can take a screenshot of this image. And I didn't say when Diophantus has passed away, because much later, actually, Metrodorus, around the year 500, came up with this epitaph in memory of Diophantus. And this is the solution goes through a Diophantine equation. And if you solve the Diophantine equation, you'll know how old was Diophantus when he passed away. Okay, so I wanted to give you a taste of like Diophantus's problems. This is very typical of what Diophantus's problems look like. So in book 4, problem 24, Diophantus asks the following: to divide a given number into two numbers such that their product is a cube minus its side. Nowadays, we would be more clear about the statement of a problem. They are all, the way they are stated, they're almost like riddles. But in any case, what Diophantus means is if you have a number A, we want to divide it into two numbers. So two numbers that add up to A, so for example, y and A minus y, such that the product of these two summands equals a cube minus the side of the cube. And this is our first example of an elliptic curve. That equation defines a elliptic curve. And Diophantus actually gives a solution. He finds a solution, and he finds a solution that y equals 26/27 works for the number y here. And I'll tell you how he finds it, because it actually, this is one of the earliest instances that we have of like the beginnings of the theory of elliptic curves. So in this elliptic curve for A equals 6, this is this in blue is the equation of the elliptic curve. And what he does is a solution that is actually concrete to the number 6, to A being 6, but it has all the elements of a general solution. And all his problems are of that form, that it's some very concrete problem, but the problem is general enough that if you are asked to solve it in general, you can follow his solution to find other solutions to other similar problems. In any case, what he does is he notices that there is a point on the curve, which is the point -1, 0, and uses that point to create or to draw the tangent line that goes through that point. And the equation of the tangent line is, I'm not giving it here, but you can find the equation just using calculus, which of course there was no calculus at the time of Diophantus, but still they knew how to do this kind of thing. And he finds the point of intersection of the curve with the tangent line. And that point, by the way, is going to have rational coordinates for a reason, because this is a tangent point. So there is the number of points of intersection of the line and the curve. It's multiplicity 2 here. So there's going to be a third point of intersection, which is this one. And because this is a rational point, it turns out that this is also a rational point. In any case, he finds a solution that x should be 17/9 and y should be 26/27. Great. So that is our first example of an elliptic curve. And again, that's something that shows up in Diophantus. And in general, how do we classify Diophantine equations? So if you want to study Diophantine equations like Diophantus did, what you would do is start, and this is how the book starts, with very basic problems in one variable, and then he starts working with more complicated Diophantine equations. What you would do is, well, we can start classifying Diophantine equations by the degree of the polynomial and also by the number of variables. So let's see how far we can get with that. If we just have one variable and any degree, what we have, this equation is just a polynomial equation in one variable, so one polynomial with integer coefficients. And we know how to find solutions to those. Then if we find, if we want to study Diophantine equations with two variables, so what you get is an equation in two variables, a polynomial equation in two variables, and then you can classify them by the degree of the polynomial. So if the degree of f is 1, you get lines in the plane. If the degree of f is 2, you get conics and products of lines. If it's sort of like a degenerate case, if you have a degree of f equals 3, you already get into cubics. And this, I have it underlined in pink because that is already where the sweet spot is going to show up. So there are some degenerate cases for these equations, and then the ones that are not degenerate are the smooth cubics. And it turns out that whether we can find solutions in these cases, it turns out that if you go through a basic course in number theory, the tools that you learn as you start with a very basic course in number theory are the tools you need to solve these type of Diophantine equations. For example, if you want to find integral points on lines, then what you need to know is use the theory of divisibility and actually develop the theory of GCDs, of the greatest common divisor, to figure out whether there will be integer points on lines. If you want to find points on conics and other equations of degree 2, Diophantine equations of degree 2, it turns out you already need very sophisticated machinery. For example, to figure out if there is a point, a rational point, you need something like what we call the Hasse-Minkowski theory, or the theory of like the local to global principle. And to actually find solutions, integral solutions, you need the theory of continued fractions. I'll give you an example in a minute of how to find a point on that conic. But if we go just one step farther to the degree of f being 3, if we try to find solutions of a smooth cubics, we are already stuck. So it just seems that number theorists have been sleeping on the job, and we haven't gotten very far in finding solutions, integral or rational solutions of Diophantine equations, because we're already stuck with the smooth cubics and two variables. We do not know how to do it. We have conjectural algorithms of how to do it, but we have not proved an algorithm that is proved to stop and halt and give you a solution. So these smooth cubics are actually where elliptic curves are. So this is the sweet spot of the arithmetic, in that, well, at the very least, is the very first time that we don't know how to find solutions in general. This is an example of an elliptic curve that will come up later also. Okay, so more formally, an elliptic curve is an elliptic or a field F. So F can be here the rationals, the real numbers, the complex numbers, or perhaps a finite field. Is what we call a smooth projective curve of genus 1. I'll come back to what genus means, with at least one point defined over F. So we study elliptic curves. Those are sort of like, it turns out that every elliptic curve can be given by a Weierstrass model. So it can be given by a cubic model of this form. If the characteristic of the field is not 2 or 3, for example, over the rationals or the real numbers, you can actually find an equation of this form for an elliptic curve. The smoothness, by the way, it has to be in what we call the projective plane. So we think of the affine plane, and then there are some points of infinity that we have to add, and we have to make sure that elliptic curve, these curves are not smooth at infinity also. So for example, this is an example of a curve that self-intersects, so that is not smooth, so that would not be an elliptic curve. This is an example of another curve that's is sort of like self-intersects, in that there is a cusp. And this, it's perfectly smooth in the whole affine plane, but there is another cusp at infinity. And these curves can be dealt with sort of like the lower dimensional tools that we have. So these are not problematic. So when the curves are actually smooth, that's when we actually do not know in general how to find all the rational points on an elliptic curve of this shape. Okay, so going back to Diophantine equations in general, not just elliptic curves, the solutions can be very intricate and very difficult to find, but we have those algorithms on how to find them. For example, this conic, if you want to find the integral points, so points with integer coefficients on that conic, well, there is a very simple one, which is 1, 0 is a point. But if you want something more exciting, that is both x and y are not in, none of them are 0, so that there are non-zero coordinates, then the very first solution, a very non-trivial solution of that conic, is given by these two very large numbers. And as I said, we know there are solutions, and to find them, what you end up using, for example, one way to do it is using the continued fraction of the square root of 61. So the fact that the square root of 61 can be written, the square root of 61 has what we call a periodic continued fraction. So it's a fraction of this form, and the numbers that we put here in the sort of the diagonal are these numbers. And then once you get to 14, it repeats again and starts with 1, 4, 3, 1, 2, 2, and so on. So it turns out that this infinite continued fraction, you can cut it off. So if you do 7 or 7 plus 1 or 7 plus this fraction, those are called convergents. And those convergents help you find, among one of those convergents, or using those convergents, you can find a solution to what we call a Pell equation, which that's an example of. So this is just to say that the Diophantine equation, some of the integral solutions are very hard to find, but for degree 2, degree 1, we know how to do it. There are other Diophantine equations that are extremely hard to find, but that can be reduced to Diophantine equations that we know how to find. So for example, I'm not going to state here Archimedes' cattle problem. The Archimedes' cattle problem was proposed by Archimedes. I don't know why, some sort of like huge challenge to other mathematicians of the time was to, I'm not going to state it, but it reduces to this Diophantine equation, which is a system of Diophantine equations, which is, there are two parts to Archimedes' problem. This is sort of like solve the first part. And once you know the solution to this, you have to solve the second part. And it is incredibly difficult to solve, and it was not solved until 1880, I believe. Somebody called Amthor proved that there is a solution and found an actual solution. If you solve the first part of Archimedes' problem, that actually leads to solve the second part. It leads to a Pell equation, which again, they are complicated solutions, but we know how to solve them. So they did that. And it turns out that the simplest solution to Archimedes' problem, or how many cattle animals you need for the problem to be solvable, it turns out that the solution would involve more cattle than there are atoms in the entire universe. Okay, so very complicated solutions. Much more recently, we actually did not know if 42 was a sum of 3 integral cubes, so the cubes of 3 integers. 42, of course, has a role in popular culture through Douglas Adams's books. 42 was famously the answer to the ultimate question of life, the universe, and everything. And it turns out that, well, 42 was also special because out of the integers, I think up to 100, there were 2 integers left to figure out if they were expressible as the sum of 3 cubes. And in 2019, Booker and Sutherland found a solution, which is this large. By the way, this is not an elliptic curve, but it's called what we call an elliptic surface. So it's a family of elliptic curves in a sense. So why I'm claiming also that elliptic curves are somewhat in the cognitive sweet spot. And what I mean by this is that there are many problems in number theory and otherwise in other areas of math where our power to state problems and problems that we're interested in and problems that we can think about and also that are already challenging enough that we that do not have a straightforward solution, that is where elliptic curves reside, in that sort of cognitive sweet spot of problems that are easy to state but already very hard to solve. So let me give you some examples. Some very natural problem to ask is, for example, find are there any cubes, any integers that are cubes and that are exactly 1 more than a square? That's something very easy to state that reduces to an elliptic curve. So squares that are 1 more than a cube. So for example, that's a question that is an elliptic curve. That's a short Weierstrass form. It's smooth. So that is an elliptic curve. And through the theory of elliptic curves, which I will not do here, it turns out that the only squares that have that property are 0, 1, and 9. 9, for example, being 8 plus 1. And there are no others. And in fact, there are no others even among the rational numbers. So there is no rational number which is a square and it's 1 plus a cube other than these 3 rational numbers. For example, are there any consecutive non-zero integers whose product is a perfect square? Another natural question that leads to an elliptic curve. So this would be a square that is the product of 3 consecutive numbers. And you can actually do a change of variables. So you get a little of a cleaner equation. So if you change variables like this, then you get y squared equals x cubed minus x. And that is an example of an elliptic curve. It's an example actually of what I study for my research, which is elliptic curves with complex multiplication, which are elliptic curves with extra symmetries. Okay, so through the theory of elliptic curves, it turns out there are none. There are no non-zero integers. You see that there are, of course, there are solutions, which is, for example, -1, 0, and 1. Those are 3 consecutive integers whose square is 0, which is a perfect square. But if you require non-zero integers, then in fact, there are no solutions. And in fact, also there's no solutions among the rational numbers other than with a 0 in them. Another problem that is very easy to state at our sort of like cognitive mathematical level is that of what we call the congruent number problem. Is there a right triangle with sides of rational length and area 6? Well, yes. For example, the Pythagorean triple 3, 4, 5 gives you a triangle that is right and gives you an area of 6, right? How about area 5? That is already a challenging problem, and is in fact that was solved by Fibonacci in the 1200s as a challenge by no other than the Holy Roman Emperor challenged Fibonacci to find a solution of the problem, congruent number problem for 5, and Fibonacci found this triangle, the 20/3, 3/2, 41/6. Is 1 the area of a right triangle with rational sides? It took all the way to the 1600s. Fermat proved that no, that is not the case, and this is in fact the this is an application of his theorem, Fermat's last theorem, for the case of the exponent 4, which is actually the only case of Fermat's last theorem that Fermat actually proved. And how about area 157? Well, yes, it turns out that the area of 157, it is the area of a right triangle with rational sides, and that was in the 1900s. Zagier proved that that is the case. And it turns out that this problem is related to elliptic curves because N is an area of a right triangle, even only if this elliptic curve has a rational point with y non-zero. So that's a connection with elliptic curves. And for example, for 157, Zagier found a point on the elliptic curve, and then he found the simplest rational side triangle, a right triangle with rational sides. And the simplest such triangle is the ABC with these A, B, and C, which, as you can see, is phenomenally complicated. If you cross out right triangles, so how about triangles? Just triangles with sides of rational length and area n. Surely that's a much more general problem and should be related to something more complicated than elliptic curves. It turns out that it also goes to elliptic curves. So such a triangle with such sides of rational length and area also rational, those are called Heron triangles. And for example, n equals 1 is the area of a triangle, not a right triangle, but is the area of a triangle. And this is one example, 3/2, 5/3, 17/6. Euler already knew that every number is the area of such a triangle, not necessarily right, but one with sides of rational length. And it turns out through some work of Goins and Maddox that they are also related to elliptic curves. So a number n is the area of a Heron triangle, even only if there is a rational number t, some other parameter, such that this elliptic curve has a rational point with y not equal to 0. If you put t equals 1, then you get the case of right triangles that we saw before. And you can, using this connection to elliptic curves, there's one easier way, much easier than what Euler did, to prove that every number n is the area of a Heron triangle. So here is another problem that is just very, very basic in elementary geometry, and that is also very much related to elliptic curves. Of course, Fermat's last theorem was very much related to elliptic curves, and much of the fame of elliptic curves actually in the late 20th century and today comes from the connection to Fermat's last theorem. So Fermat's last theorem, Fermat claimed in the margin of the book of Diophantus of the Arithmetica that he was reading, he wrote that this equation, sort of like trying to generalize Pythagorean triples to higher exponents, that this equation actually has no integral solutions, non-trivial integral solutions. So if x, y, or z are not 0, then there are no other solutions to this equation. It turns out that for n bigger than 2, of course, for 2 there are solutions, for n bigger than 2 there are no solutions, or Fermat so claimed, without a proof. He claimed to have a wonderful proof, but almost surely he had an incorrect proof, if any. At any rate, here is the connection to elliptic curves. For example, the exponent 3 this equation over the integers, if you divide through by this z cubed factor, then what you get is this equation, and this equation actually defines an elliptic curve over Q. This is a smooth cubic that has at least one point. So it is an elliptic curve, and using the theory of elliptic curves, you can show that there are no rational solutions. So you would prove Maslows theorem for the exponent 3 just using elliptic curves. But more interestingly, for this equation, which is, again, for 3 is an elliptic curve, but for higher powers are not elliptic curves. There are curves of higher genus that we'll talk in a moment. The solution also went through elliptic curves by an interesting suggestion of Hillegaard, and then elaborated by Frey, that if you have a non-trivial solution of Maslows theorem, then we should be looking at this fabled elliptic curve. So if there is a solution, there would be this elliptic curve with a very strange property. This elliptic curve would be what we call semi-stable, but it could not be possibly modular. I'm not going to define what those things are, but the last step was Andrew Wiles and Taylor Wiles. They proved that what we call the Taniyama-Shimura-Wei conjecture, that every elliptic curve over Q, they proved the semi-stable case, that every elliptic curve is actually modular. But if this existed, there would be a non-modular elliptic curve, and that would be a contradiction. So that elliptic curve cannot exist, so this solution cannot exist, and that proves Fermat's theorem using elliptic curves. Now, going back to Diophantine equations and how complicated the integral solutions are, one can think, okay, as I said, we do not have an algorithm for elliptic curves, but maybe there is an algorithm. Maybe there is an algorithm. David Hilbert dreamed of an algorithm that works for every Diophantine equation. So Hilbert, in the year 1900, at the turn of the millennium, at the turn of the century, he proposed a list of 23 problems, and the number 10 of his problems was this problem that I stated here: to devise a process according to which it can be determined in a finite number of operations whether the equation is solvable in rational integers, or in the integers. And this we know how to do for lines, we know how to do it in conics, but we do not know how to do it with the smooth cubics, for example, okay? But that is not what Hilbert asked. Hilbert asked for one algorithm that would work for all of them, and not just for these, but for any Diophantine equation. And whether this exists or not, that was a question that later in the 20th century, surprisingly, was answered negatively by logicians. So the logicians seem to be hell-bent on giving Hilbert an ulcer in the 20th century, and several problems that he thought were that we would find a solution, the logicians showed to either be through the incompleteness of axioms, or that one could not prove or disprove. But in the particular case of Hilbert's 10th, whether there is an algorithm to find Diophantine equations, Davis, Matijasevich, Putnam, and Robinson, and Julia Robinson, showed that that is not possible, that if you have a Diophantine equation over the integers, there is no algorithm that can determine whether that Diophantine equation has an integral point on it. We'll come back. I need a little bit more about elliptic curves to show you how elliptic curves actually play a role in this, have a very, very special role to play in this question. But I need to show you a little bit more about elliptic curves first. Let's go to geometry. So why do I say that elliptic curves play, they are in the sweet spot of geometry? So if you look at complex geometry, complex algebraic geometry, or for example, curves, complex algebraic curves, are classified by their genus. The genus here is the dimension of the space of regular differential one forms on the curve. So that dimension of some space of differentials it turns out that plays a very significant role in how we study these curves. So if you have a curve that is given by an equation, we can let's think like we were thinking before of our Diophantus equations. Let's just write our curve and suppose still that it has integer coordinates, but now we are thinking about all the complex solutions to our equation. So that curve, it turns out, once you go to the complex numbers, that is a complex manifold. And according to their genus, when G is 0, when this dimension is 0, then what you get is something like a sphere. When the genus is 1, you get a torus or a donut like this. So there is one hole. And when G is bigger or equal to 2, you get some other complex surface with some G holes. Okay. And it turns out that that is very much related. This classification of like this, these curves as complex structures has a very deep connection with the arithmetic. It turns out that if you have lines and conics, so if the degree of your curve is 1 or 2, which corresponds to genus 0, so when your curve has genus 0, it turns out there's a dichotomy that either you have no rational points whatsoever, or you have infinitely many. And once you have one, you can actually do what we call stereographic projection to find them all. Great. Here, in the case of cubics, I wrote cubics plus because there are some degree 4 equations that are actually birational to in bijection to cubics, but basically cubics, that is the case of genus 1. And this is the sweet spot of geometry because everything can happen. You can have no points whatsoever. You can have a finite amount of points. So you can have like 12 points and that's it. Or you can have infinitely many rational points. So this sort of variety, that doesn't happen in any other case where you can have non-finitely many. I guess none is finitely many also, but sort of like absolutely just empty set, some finite number, or infinitely many. That can only happen in the case of genus 1. Great. So what about higher genus? So if the degree of your polynomial is homogeneous degree higher than 4, then the genus jumps to 2 or more, and then you cannot have infinitely many points. That's what we call the Mordell conjecture, which is now a theorem of Falting's. And there can only be finitely many points. And in most cases, now we know also that in average, in most cases, there are no points in these curves. So here are some examples that I've just written down a few examples of what happens in genus 0. So for example, this curve has no rational points, but this one has infinitely many, and we can parameterize them using stereographic projection. If the genus is 1, we can have no points whatsoever. We can have, this is by the way, the Fermat case, the Fermat curve for exponent 3. There is actually just 2 rational points and 1 more at infinity. By the way, this is a cubic that is not in what we call Weierstrass form at the beginning. So if you want to put in Weierstrass form, that's the Weierstrass form. Or you can have, like in this elliptic curve, you can have infinitely many rational points. Okay. The point, what is it here? 27 minus 2, that's 25. So the point 3, 5 has order, or you can generate out of that infinitely many points. And for higher genus, for example, this is a curve of genus 3, and there are absolutely no rational points. And this is a curve of genus 2, and it has 3 points and 1 more at infinity. Okay. So, but the beauty of elliptic curves is that out of all the curves of genus 1, you can put a geometric group structure. You can add points on your elliptic curves. So if you have genus 1 and you have at least 1 point, that's why elliptic curves will require at least 1 point that can be your 0 for your group structure. So you can add things. So once you have 1 point, you can put a geometric group of structure on the points, and which is defined like Diophantus did. So if you have a point P and a point Q, you draw the line through P and Q, find this point, and actually for reasons so that this addition is associative, for example, we reflect with respect to the axis of reflection of symmetry of the elliptic curve, and we call this point is the one that we call P plus Q. If you want, you can also double points. So if you have Q, if you want to double it, then what you do is trace the tangent line, find the intersection point, reflect it, and then that point will be 2Q. And out of one point, I can find new points on my elliptic curve. Okay, and using this, you can find more and more points. And what turns out is that, so using these laws of, in the image behind me, you can still see that addition and doubling. Using doubling and addition, if you have a number of points, then you can generate all the points that you can generate using those two operations. And what Mordell proved in 1922, in fact, 100 years ago, on his thesis, Poincaré suggested this. Poincaré sort of like thought this was true, and Mordell proved it, that in an elliptic curve, there is a finite set of generators that through these secant and tangent constructions, you can find all the other points. So what that means is that the set of rational points on the elliptic curve, this is how we denote all the rational points, is what we call a finely generated abelian group. There is only a finite number of generators that will generate all the rational points. And using algebra, what that tells us is that there is two pieces to an elliptic curve. There is a finite group of points of finite order, which we call the torsion subgroup. And then there is a number of generators of infinite order, but some finite number that which we call the rank of the elliptic curve. By the way, we know a lot about this group. What are the possibilities? Mazur proved that there is exactly 15 possibilities for the torsion subgroup over Q. And for example, Noam Elkis has shown that the rank can be at least 28. But we don't know any elliptic curve with a rank higher than 28. And there is sort of like this controversy or this back and forth between mathematicians, people who think that ranks should be or will be unbounded, can be arbitrarily large, or people that have proposed heuristics that say that the rank is actually bounded. There's a limit of how big the rank can be. And maybe 28 is the largest rank, who knows? Okay, so now that we know about ranks, let me talk to you about Hilbert's 10th again. So Hilbert's 10th problem, remember, it was whether there is an algorithm to find a solution to a Diophantin equation to determine whether it's a solution in the integers of a Diophantin equation over the integers. So you can change the rank of definition of your Diophantin equation. So for example, if you replace the integers by the Gaussian integers, so by a plus bi with a and b integers and I squared equals -1, this is a new rank. And now you can ask, is there an algorithm to determine if Diophantin equations over z adjoin I have a solution over z adjoin I? And that is a very different problem. That's a different problem than Hilbert's 10th. And the solution of Matyasiewicz and company does not apply here directly. So we have this question, and it turns out that elliptic curves play a very significant role here to decide Hilbert's 10th over all the ranks. So work of Deneuve, Fides, Schoenbetak, and Poonen imply the following. Suppose you have a number field F. Inside a number field can be, for example, Q adjoin I, so the Gaussian numbers, and inside that there is a Gaussian integers. So for example, for Q adjoin I, if there is an elliptic curve over Q such that when you go up to that other field and look at how many rational points are over this new field, if it turns out that the rank is the same over Q than over this field and the ranks are equal 1, then there is no algorithm over the rank of integers of that number field. So here I have an example of an elliptic curve. This is an elliptic curve over Q, and the rank over Q is 1. But if you go up to this larger field, Q adjoin I, the rank is still 1. And therefore, Hilbert 10 is also not solvable over Z adjoint I. There is no such algorithm. So, so it turns out then that you can solve, if these elliptic curves exist, which we think they exist, for every number field F, we think there is such an elliptic curve, and the people have proved it in many cases now, then we know that Hilbert's 10th will also be false over those ring of integers. So here is a very interesting connection of elliptic curves about all Diophantine equations. All right, how about in complex analysis? They also play a fantastic role in complex analysis in the theory of Riemann surfaces. So that is a central object of study in complex analysis, that of a Riemann surface, which is a connected one-dimensional complex manifold. So let me give you an example of a compact. So a complex manifold, for example, the complex plane is a complex manifold, and a compact Riemann surface, this is not compact if you just think of the complex numbers. So what we do is a one-point compactification. Think of the complex numbers wrapping up and just leaving one point at infinity, and then add one more point at infinity. That gives me what we call the Riemann sphere. And that is a one-point compactification of the complex numbers, and it gives you a Riemann surface that is compact. And it turns out an amazing fact is that compact Riemann surfaces, this complex manifolds, any complex manifold that is compact, connected, and one-dimensional, it turns out there are in bijection with complex and smooth projective algebraic curves. So, for example, this compactification of the complex plane corresponds to just the line, the projective line over the complex numbers, which is, by the way, when we talked about genus of algebraic curves, this is a genus 0 algebraic curve. So what happened? What other compact Riemann surfaces are there? We have classified them. Here's another source of Riemann surfaces that are compact are the following. You take the complex plane, you draw a lattice. So this sort of like, you see these points that forms a lattice on the plane. I'm going to generate lattices by 1 and tau, some complex number tau. And if you do the quotient of the entire complex plane by that lattice, you get what is another Riemann surface that is of flat curvature. So it's of 0 curvature. And it turns out, by what we call the uniformization theorem, is that every Riemann surface like this is actually an elliptic curve. There is an elliptic curve as a complex algebraic curve, an elliptic curve, genus 1, that is in correspondence with this Riemann surface, that is isomorphic to that Riemann surface as complex manifolds. You can do other structures in the compact Riemann surfaces. The other complex Riemann surfaces come from quotients of the hyperbolic plane. So you take the upper complex plane, and then if you have a friction group acting on that complex plane, you do the quotient, and these ones that have negative, the ones with negative curvature, those corresponds to the curves of genus bigger or equal to 2. And those are the rest of Riemann surfaces. So the fact that these ones, the only ones that have 0 curvature, are the elliptic curve, that makes elliptic curves play a very important role. But it turns out that even for the higher genus Riemann surfaces, elliptic curves also play a role. So it turns out that if you start with one of these quotients and you look at the holomorphic differential forms in here, that leads to the concept of modular forms attached to this function group. And it turns out that in some special cases, but in many cases, these modular forms actually correspond to elliptic curves themselves, which is part of the modularity, which was part of the proof of Vermasler's theorem. So elliptic curves actually are sort of like pieces of the complex structure of these higher genus curves. By the way, this concept of modular forms has also been elaborated into algebraic topology by Hopkins, Mahold, and Miller, to define what they call the topological modular forms. So there is some sort of analog of elliptic curves or modular forms in algebraic topology here. By the way, there is also a very cool relationship between these and art, which is that if you take out the circle model of the hyperbolic plane and you look at geodesics in the plane, then you can do tessellations of the complex plane. And for example, Escher, the artist, has like very cool pictures that he did using this concept from these portions of the hyperbolic plane. All right. So in the sweet spot, by the way, so going back to elliptic curves, remember, so quotients of the complex plane by lattices are over just up to isomorphism of these Riemann surfaces. They are in correspondence to elliptic curves by the complex numbers under isomorphism, and we can actually parameterize all of them. It turns out there is one elliptic curve for the complex numbers for each complex number. I can actually tell you how to go from one to the other. So if you have a Riemann surface like this, then it turns out there is a formula for the elliptic curve that it is isomorphic to, using what we call elliptic functions. And giving an elliptic curve, you can actually give a complex number that tells you what is the complex isomorphism type of that elliptic curve, which is called the J invariant, which is also given by these elliptic functions. And so the J invariant, because it's some periodic function, you can actually give it a Fourier expansion in terms of e to the 2 pi I tau, and you have what we call the Q expansion of the J invariant, which again is just a Fourier expansion of the modular J invariant that classifies elliptic curves up to isomorphism. But it turns out there is a very surprising and amazing connection to group theory that was discovered in 1978 by John Mackay. What he discovered is that the numbers that appear, not 744, although that appears in other cases of this theory, these numbers are actually sums of linear combinations of the dimensions of irreducible representations of the monster group, which is the largest of the sporadic finite simple groups in group theory. So this amazing connection was just like blew people's minds. This was called monstrous moonshine, that somehow the monster group is shining in here. You can see some reflections of it in the J invariant somehow. And later, Conway and Norton came up with a specific conjecture of why this was happening. And Borcherds proved that connection in 1992, earning him a Fields Medal for that particular work on moonshine. Okay. By the way, I wanted to go back to the number e to the pi square root of 163. It turns out that this elliptic curve is to blame for that. This elliptic curve, the tau for the lattice is this tau, and if you put this tau here, then you get that this number is this number, and it has to be very close to an integer because the theory of complex multiplication, which this elliptic curve has, complex multiplication tells you that this number is an integer. So this number has to be very close to an integer. These are very small numbers. So it explains that. By the way, there is more connections between these lattices and art. There is a very beautiful picture of Escher where there is this guy is in a gallery looking at a painting, and in the painting there is a harbor, and in the harbor there's a gallery, and in the gallery there is a person looking at the painting. So this painting that is sort of so amazing. Escher did not complete the painting. There was a step missing in there. I'm not sure if he just didn't know how to complete it, but the Smith and Lenstra, using elliptic curves, thinking of this as drawn on an elliptic curve, it turns out that they were able to complete the picture. So you see they were able to complete the drawing using elliptic curves. Okay, let me just talk very briefly. How long do I have? Like another 5 minutes?
Another 5 minutes is fine, yes. But we have to finish by 7, so good.
Great, thank you. So by the way, so given an elliptic curve, how do you find this tau? it turns out that this tau has to do with line integrals on this elliptic curve. And that brings me to actually, why are elliptic curves elliptic? Why are they called elliptic? Are they related to ellipses? So it turns out that in physics, ellipses were very hot in the 1600s due to Kepler's laws. So Kepler's law says that planets move in elliptical orbits around the sun. So it is natural to ask to compute arc lengths of ellipses. So Newton, Euler, and many others computed such things in terms of infinite series, but later people started to wonder how to actually read them in terms of integrals. So if you want to find the circumference of an ellipse, this is the integral that gives you that. And if you make a change of variables, you get to this integral. And it turns out this integral, you see this is a square root of this. What it means is that you are doing an integral on an elliptic curve, sort of one of these periods, one of these integrals that I was talking about before is what is happening here, that defined the length around an ellipsis, the circumference. What you're doing is an integral on an elliptic curve. Similarly, you can actually do arc lengths or put this as a function of the angle that you're going by. And this function, if you, Jacobi and Abel, what they did is study the inverse function. In terms of the inverse function, the inverse functions are elliptic functions that came up when we were trying to go from lattices to elliptic curves. More recently, though, in the later 1900s, in string theory, elliptic curves also show up in physics because string theory needs higher dimensions. So string theory says that the universe at the most, so the fabric of the universe is on Calabi-Yau manifolds, maybe 6 dimensionals, maybe 23 dimensionals, depending on the string theory. And well, in physics, they love studying vibrations of strings. That's a very classical topic. Well, if you try to vibrate a string, what you usually, or when you try to study motions of particles, you look at closed loops. So if we do a closed loop of a string, what we get is, well, there is an elliptic curve that is the entire motion of the string. And then what you want to do is, well, try to analyze what sort of vibrations you could have, a string could have in a Calabi-Yau. So how do elliptic curves fit in Calabi-Yaus? And that brings a lot of questions in string theory that are related to the algebraic geometry of elliptic curves in higher dimensional varieties. Finally, I just wanted to mention the relation to Bitcoin in the last minute. In complexity theory, elliptic curves have a very natural sweet spot in there, and it comes from the advent of public key cryptography and public key exchange, where you have some public keys that are combined to a shared secret key. Diffie and Hellman came up with an algorithm to do this kind of sharing of keys. Let me just, I'll have these slides will be available in my website, so you can go back to them. But there is a way just on integers modulo p on how to give out some public key and that can be used to compute a private key. And the strength here is the discrete log problem that is very difficult. If I just give you a power of a number modulo p, it's very difficult to figure out what was the number I raised a power to, or what was the exponent in here when p is very large. And now we want to replace the integers modulo p by other groups that offer efficiency, but also greater security. If you start from an abstract group, using algebraic groups is natural because, well, if it's given by some algebraic equations, it's easy to store those equations on a computer. And algebraic groups with a group structure that naturally leads to a billion varieties, of which the dimension 1 are elliptic curves. And in fact, higher dimensional varieties, they don't offer a lot of greater security in terms like the balance between efficiency and greater security. According to cryptographers, it seems that elliptic curves is really the sweet spot of that balance between efficiency and greater security. So you can replace the role of Z modulo P and the Diffie-Hellman by an elliptic curve and create secret keys that are using these elliptic curves. So for example, WhatsApp uses such security. Let me just say that, well, factorization also elliptic curves plays a role, but in particular, Bitcoin and PS3, what happened is that they were using some form of digital signature that is also related to elliptic curves, but in the implementation, you have to be careful. There's this exponent k that you have to choose, and in both cases, that implementation was not done correctly, which led to vulnerabilities that people were able to break this digital signature that comes from elliptic curve cryptography. So in any case, are elliptic curves in the sweet spot? Maybe it's just the law of small numbers. We are in many of these areas, we're in the infancy of mathematics, in how we are still studying the Diophantus equations of very low degree, number of variables, Riemann surfaces of low genus, abelian varieties of low dimensions, weak computing power. All those small numbers lead to elliptic curves, but maybe as mathematics grows a little wiser, we will step out of the sweet spot of elliptic curves into realms of other higher dimensional abelian varieties. Okay, so I think I'll stop there. Thank you.
Thank you very, very much for this very interesting and very clear talk. I would like to open the floor for our attendees. If you have any questions, please, you can raise your hand and you can take the stage.
Yeah, I would love to answer any questions by the audience.
I have a question. Kamal, you can go ahead.
Oh, sorry, I was just applauding. I enjoyed the talk a lot. I don't have any added questions to ask right now. Let me see if I can come up with some.
Thank you.
I actually have a question for you. At the beginning, you mentioned in the book 4 of Diophantus about the number where you can write as a sum of two numbers such that their product is a cube minus x. What is the motivation for that, actually? Is there any geometric motivation or just...
For the problem itself?
Yeah.
I would have to look back to see what the problems before that are, but it really seems that the problems in Diophantus are not very well motivated. There are many problems that are just sort of like strange problems, just like that. The statement seems strange, and I wonder. I'm not a historian, but I wonder if, like, for example, many of these problems were probably floating around. Many of these problems come from challenges from one mathematician to another. Do you know how to find this? Because I know how to do it. Do you know how to do this? So some of these problems that to us, all of a sudden, they just seem like completely unmotivated. Some of these problems were around for a long time before people solved them. For example, the problem of the congruent number problem that I mentioned, Fibonacci was challenged to solve. That problem had been around for hundreds of years, and it appears in other parts and other texts and other like documents that have survived. So some of these problems were problems that maybe either people didn't know how to solve at the time, or they knew how to solve, but Diophantus finds a better solution. So that's my explanation for some of these. I don't think there is a very clear motivation of why this particular problem, for example, he was trying to solve. Sometimes it seems like he's solving the problems he knows how to solve.
I see. Okay, thanks. Any other questions from our attendees, from the audience? Okay, thank you very much, actually, and looking forward to having you here in Beirut. So
I would love to come.
Okay, thank you.
All right, thank you very much.
Okay, bye.